Hi, welcome everybody to this webinar, which is part of the OPCUA FX Professional Series. So, as you probably know, because you found somewhere the link to this webinar or to the recording, the UAFX Professionals is a group that tries to teach and educate people on OPCUA and specifically UAFX. Which is a sort of a profile of OPCUA to have a more engineering workflow around OPCUA communication and modeling. Today, this session is on general OPCUA and UAFX networking topics. Specifically, I will dive into achieving performance and convergence with UAFX and OPCUA. We have a mix of what's in the standards already, what we currently work on, but also a few measurement results that you get a feeling on what we try to solve and where we are heading to. So in general, feel free to follow us on LinkedIn, subscribe on YouTube, and share the videos. So it's a full series. We're basically in the middle of a full series of videos. There have been videos in the past on TSN, on the UAFX architecture already, and there will be further videos coming out. So just follow us on LinkedIn to make sure you don't miss future videos. So let's start for this webinar today, focusing on OPCUA, UAFX networking. And maybe let's quickly start with a short introduction on my person, that you get a feeling on why I'm the right person to talk about this topic. Since 2012, I am with the company Belden, or basically better known as the Hirschmann brand of Belden, Hirschmann Automation and Control. I'm in Germany, but we're a global company doing network equipment, active and passive solutions. So a lot of networking for industrial market. Industrial includes any kind of from process industry, discrete manufacturing, energy business, but also transportation. My role is technology architect for time-critical and converged networks. That means I have a focus on time criticality of applications, on networks that share different types of applications with different technologies. So today we mostly will talk about Ethernet and IP networks, but in general, this also includes any wireless, so Wi-Fi or 5G networks, but also MPLS-TP networks. And in general, as you probably know, OPCUA itself is independent of the technology on the bottom, so there's a physical technology, and therefore I have quite a good set of expertise in all these different technologies to ensure what we define in OPCUA can be applied to any kind of network, having in mind that most networks will be Ethernet based. In the OPC Foundation, I'm active since 2019 in all kinds of networking topics. So specifically, or mostly in part 14, which is for PubSub, the part 22, which is the base network model, but also in UAFX in part 82, and then the conformance unit is 84, but also a little bit 81. And in parallel, since 2020, I'm a PhD candidate in the field of network security, at the Esslingen University and the University of Tübingen. So maybe, that explains some approaches that I take for the presentation of topics. So let's dive into the agenda of today. What can you expect from the next 45 to 60 minutes? First, I will quickly go over networking in OPCUA and UAFX. There have been sessions on similar topics already, so I will keep that brief. I will highlight what options are there, what UAFX specifies on or builds on. And if there are further questions, we can take that then to the Q&A or have a dedicated session on more details there. Today, the focus is then on increasing the network performance. So really looking at where in the network do we lose performance and what is available to increase the performance. And then a topic or a section on enabling network convergence. And with convergence, we mean aggregating different types of applications on the same wire or the same physical media, the same accounts for the wireless networks as well. And at the end, we have a short wrap up and the Q&A session. So let's start with OPCUA and UAFX networking. So on that slide, I quickly want to show the most important types of communication available in OPCUA, and want to highlight where we focus on today with our talk. So in general, there is client-server communication and publish-subscribe communication in OPCUA available. Client-server means you have a server somewhere running and the client connects and then dynamically requests data from there. You can either do that with the native OPCUA server or also now via REST API. So if a device offers a REST API for OPCUA, then you can also connect with a standard REST client and interact with that. And there's a Swagger API definition for that available. So you can integrate OPCUA data models in any kind of IT infrastructure with REST. The second part is the publish subscribe. And for the publish subscribe, there are three main types of data exchange. OPCUA PubSub, which we will focus on today. That is the main part of what we're going to talk about. And then there's also MQTT and AMQP for more IoT and IT integrations. The OPCUA PubSub is really the crafting a raw UDP Ethernet message, cyclically publishing that either unicast or multicast to subscribers. MQTT and AMQP then have brokers in between. So we focus on OPCUA PubSub. In general, something to always keep in mind, OPCUA is very powerful in the modeling. The information model, that's a huge benefit of the OPCUA. In general, we have a large set of companion specifications, but also you can customize information models quite well. And there's a wide range of communication categories such that you can seamlessly integrate that very powerful model into different environments and solutions. Okay, so now let's have a look at OPCUA PubSub. On the left-hand side, I copied two pictures from part 14. They very briefly show what PubSub does. So on the publisher side, you have the information model here in blue, and then you define how the data is put together in data sets and then writer groups into the packet. The packet is then transmitted over the network. And on the other side, there is basically the same configuration, but vice versa. And you pull out of the frame at predefined locations the variables and put them again into your information model. So now on both sides, you can have any other kind of application running that utilizes the information model, either by pushing data there or by reading data. And the PubSub takes care of the exchange of the variables. And you can craft messages where all the data sets go all into the same subscriber, or maybe multiple subscribers receive the message and everybody just takes a piece out of it. So there are different options available, but in general, that's the path to keep in mind, and that we have a very structured way of crafting the messages and then receiving them on the other side. Now, if you look at OPC UA FX, they build on the PubSub with their connections. So OPC UA FX connection builds on top of PubSub. But as you can see with the red arrows, they combine multiple PubSub connections within a UFX connections. Because what PubSub can do is a very flexible exchange of data, but it doesn't reflect typical industrial exchange with heartbeats or sending data, receiving data as part of a control loop. And therefore, these different types of communications are modeled all in UFX connections. That means UFX connections at the end potentially result in multiple PubSub connections to be established underneath. So UFX uses the cyclic PubSub communication with UDP by default, and we will have a look at what UDP means in a second. And options for Ethernet with a fixed header layout. So the structure of the frame is always exactly the same. And additionally, UFX defines logical connections that can include multiple PubSub connections underneath. And that is just important to know. In the following, I will very often talk about the raw PubSub connection. So just keep in mind that a UFX connection can include the same thing, but just bidirectional. So far to the basics on the communication. And now I would like to have a look together with you on how to increase the network performance. And there are different pieces where we first need to understand where we lose the performance. And the first thing that I want to draw your attention to is the difference between UDP and Ethernet on an end device. So here on the left-hand side, you have now the structure that we have our OPCUA PubSub stack on top. Then we have an IP stack, typically in the operating system below. And then we have the Ethernet stack or then the network driver on the lowest layer. And if you now send an OPCUA PubSub message, then you send this UADP UDP packet to your operating system normally. In the transport profile URI, in the configuration and information model, you would add this transport profile URI to indicate that you want to use UDP UADP. So UADP is the format of how OPCUA crafts the message. UDP is the addressing. And therefore, in the address, you will also see opc.udp, and then you either have a multicast IP address or a unicast IP address and the port where the other side is waiting for the messages. Now, what happens in the operating system, if you pass an IP packet, the system needs to figure out which MAC address to talk to. So on the wire, you always need the MAC address first. And therefore, the IP stack either has in the ARP table, in the cache, the correct mapping of IP to MAC address. Or if not, for example, if it's the first communication or first communication since quite a long time, the system needs to do an ARP request. So basically asking in the network which device has the IP address and basically requesting the MAC address for that. And this piece in the middle can cause quite some delays because the ARP request is non-deterministic. So it depends on how quickly the opponent responds. And if the opponent responds at all, maybe there is some misconfiguration. So this could cause some additional delays. There are ways to improve that by just fixing the ARP table, adding the entries statically up front. But just be aware of this kind of procedure in the middle, that this can cause a delay. Alternatively, if you use UADP Ethernet directly, then of course you need to choose a different profile URI. You also address the host with a MAC address here. You can add VLAN ID and PCP here, but we show you a second path for doing that in a second. And then the pub/sub stack directly sends the frame out. You do not have such an intermediate step. In general, when we talk about the performance of an end device, the UDP versus Ethernet is an important topic, but it's not the only topic. So as I already said, the UDP might require ARP requests before transmitting the packet, depending on the state of the local ARP table. So this can lead to unpredictable delays that you need to be aware of. But there are other pieces playing into these latencies as well. So the general stack implementation is also a very important thing. There are different stacks available on the market. So for you, it's just important that you understand the different steps between the stack, crafting the message, and the message really being on the wire, and that you choose the right mechanism then for your system. And you also need to evaluate the pub/sub stack itself, how performant it is, because you can also have a lot of delays up here. So that's just one thing to highlight. So now let's look at a broader scope in the network on where we could lose performance. The first thing that I already talked about is the transmission delay. So the end device has certain delays that you need to be aware of that impact on your total end-to-end delay and therefore performance. Additionally, in a network, you have cable delays. Cable delays are typically very small. We have I show you in a second what the cable delay depends on, but you can ignore the cable delay typically. Then you have the processing delay of all the switches in between, or even routers, firewalls in between, depending on your architecture. The processing delay depends on the hardware within the switch or router, sometimes for firewalls, even software. Then you have a store and forward delay that results from the packet sizes and link speed. Alternatively, maybe you have heard of cut-through forwarding, so without storing the whole frame and then forwarding, but directly forwarding when you just receive the header. That also has a delay, which is a lot lower, but it's not a standardized feature yet. IEEE is working on that. So far, it's just a custom feature. So we are not going to talk about it. And then the most important feature, the queue delay. The queue delay, that is the one that we want to target with the mechanisms that we select with TSN in the network. And the queue delay is where we can gain the most performance. So all the other factors are basically static. They are there. You need to account them in the network, or the network management tool needs to account for them. Hopefully not the user needs to do that. But the queue delay, that is the most important one. So here a quick table to summarize what the delays depend on. As I said, the transmission delay is the end device OPCUA stack. And then we have the cable delay, which depends on the material and length of the cable. Fiber is typically speed of light, but then you also have the SFPs. So the modules that you put into the switches, they have latencies. It's just important to know that it's there, but typically you can ignore it. You have a processing delay of the chips in the switches. That can range from 1 to 6 microseconds. At least that's what we measured. So we did quite a few measurements on different types of hardware. If you then have software firewalls, then you are even higher than 6 microseconds. But that's for a switch roughly what you can estimate. Then you have the store and forward delay. This depends on the frame size and link speed that you have. And there we have here a short table. We are not going through the table now, but if you're watching the recording or have the slides afterwards, you can pause here quickly and just have a look. That's just for reference. You see in the different rows, different frame sizes as examples. So we even have the jumbo frames in here, but we have also the smallest frames available. And then we show for different link speeds how long a frame takes for the store and forward delay. So that's basically sending or receiving the full frame is that delay indicated here with the blue bubbles. What you already see here is, and that is also one of the conclusions, or maybe not a conclusion, but an indicator. When you look at the 10 megabit and 100 megabit durations, they are quite high. And if you then say, okay, I maybe want 500 microseconds end-to-end latency, and you look at a large frame with 100 megabit, then you do not have too many hops available until you already reach that limit. But if you now directly go to gigabit, you cut down the duration by 10, factor 10. So you can have 10 times as many hops, 10 times as many interference on the path. So increasing the link speed helps drastically to improve the performance already. And if you look at the TSN standards, they have been developed in a field where most of the industry was at 10 megabit or 100 megabit. Now with the industry going to gigabit, some of these mechanisms maybe are not that relevant anymore. They still have their position and their relevance for specific markets. But in general, when you discuss TSN mechanisms, and I will show you two examples in a second, then also having the link speed in mind and these delays in mind is very important, because maybe the problem also goes away with just higher link speeds that evolve from time to time. So these are two factors to keep in mind. I don't want to argue for any of both, but just to keep that in mind. Right. And as a last delay, to finish that slide, we have the Q delay. And as I already mentioned, the Q delay, that is the one on the egress side of a switch. This is dependent on the load of the network, on the other traffic in the network. And that is where we can choose mechanisms, TSN mechanisms, to reduce this Q delay by selecting and configuring the correct features. So that's where you increase the performance of the network. So the first four are basically just there. You need to account for them, but you can't change much. The fifth one is the one where you can increase the performance. And the fifth one obviously also depends on the link speed, network load and link speed dependent. So let's have a little look at the Q delay, what that means. So here I have a figure that shows the full range of the behavior. So with the green line, we basically showcase the best case example. So forwarding the frame without any Q delay. You see that there are delays on the wire, within the switch, on the wire, within the switch. So you can't get around all the delays, but you have a best case that you can calculate. And now on such a switch here with the number 2 indicated, we have cross traffic coming in. And that traffic here, depending on what priorities they use, what mechanisms are then configured here on the second link, depending on these settings, you have a potential interference between your stream number 1 and the interfering stream number 2. And that causes that the worst case is increasing more than the best case. And here you see basically the impact of that Q delay. So the difference here is the potential Q delay that you have. More drastically, here on the right-hand side, I showed 2 measurements that we conducted. The first one is one where we configured no special mechanisms, basically. And we did send our time-critical traffic. In the best case, we achieved our green line almost. And then in the worst case, other frames here from path number 2 interfered with our traffic, we had a very strong increase of the queue delay because we injected a lot of traffic here. And you can see the range between best case and worst case is very high. And we just had 3 hops here. So imagine being a network with 20, 30 switches in one line. Now, if you choose the correct mechanisms, and correct mechanisms always depend on your scenario, but there are possibilities, and we'll look at that on the next slide. If you choose the correct mechanisms, you can bring the best case and worst case close together. And that is where you reduce the queue delay and increase the performance of your network. So let's have a look at TSN mechanisms to choose. One very dominant example is the scheduled traffic feature. Scheduled traffic, also maybe known as QBV mechanism, was defined in the 802.1 QBV amendment of Q. It's now part of the full 802.1 Q standard. The scheduled traffic defines a cycle on your egress port. And within that cycle, you can define time slots. And for each time slot, you can assign a set of priorities or traffic classes that are allowed to send in there. And what you can see, the cycle starts with yellow, then blue, and then purple. And while we are here in the yellow phase, it looks only in the yellow queues, and we only have one yellow queue in this example, and directly takes the frame that is basically ready for transmission and sends it. Then it goes to the blue phase, looks at the blue assigned traffic classes, which is traffic class 6 here, takes frame number 2 and sends it. You see that the frame number 1 could directly have been in theory sent in the beginning or here directly after frame 2, but it was not, because only the third slot is assigned to the purple traffic classes, and the frame 1 is within the purple traffic classes, so it needs to wait until that point in time. The same is for the frame number 4, which arrives with PCP2, therefore lands in, so PCP is the priority value in the VLAN tag, lands in traffic class number 2, and then needs to wait until that point of transmission. And the same is for frame number 5. Even though it's the highest traffic class, it needs to wait again for the next cycle to start. So with that mechanism, you see that you really have dedicated slots on your wire for different traffic classes. And now if you start scheduling the transmission on your end devices, and OPCUA will offer mechanisms for that in the future, then you can basically go through the whole network without any additional delays. And all the other traffic does not matter to your traffic anymore. It's just about your own scheduling of the traffic and then going through the network. All the other network load is independent. Just keep in mind, you only have 8 traffic classes available. So you need to share the traffic class with all traffic of your priority. But typically, you only have little traffic in the highest priorities. And then you have a lot of best effort traffic. A second very effective mechanism is the frame preemption mechanism that you can choose in the network. And this figure briefly summarizes how it works. The frame with the PCP value 6 arrives first here. So this is the first point in time. It's the preemptible category. The switch starts sending the frame, but then the frame with PCP 7, which is in the express category, arrives. And you see here from the right-hand side to the left, that's the beginning of the transmission of PCP 6 frame. And then at that point in time, the switch decides to preempt this transmission, send a high priority express traffic, and then resume the transmission of the PCP 6 frame. And with that, you also ensure that your critical traffic is forwarded with a high priority does not need to wait on the egress queue. So you reduce the queue delay by putting the frame on the wire as soon as possible by preempting another frame. So this mechanism also has a very good impact on the queue delay. You can assign multiple priority values to the express category. Just keep in mind, express cannot preempt express. So everything that shares the express also blocks again itself. But if you have, for example, video traffic in the preemptible, huge frames, very bursty, tough to control, still your critical control application can preempt that traffic and is more or less not disturbed by that. So now let's have a look at some measurement results for these two mechanisms. The first figure is similar to what I have shown in the previous slide. Just as a recap, depending on the configuration, and on the top you always have a bad configuration, and on the bottom you have then the good configuration. You have a range between best case and worst case. When you configure the time-aware shaper correctly and very good, you have only limited number of traffic classes together in one slot. You control the transmission point in time, and then you can go through the network in your best case scenario. The frame preemption figure is a different view that shows now a histogram. So it's not along the paths and measurement results, but it shows a histogram. And in the first figure, important is to look at the blue part. The blue part is our critical traffic. You see that we have a lot of frames clustering here at that latency. And then we have a lot of frames having a higher latency. So you see, basically, that is the best case that we can achieve. And most of the time it works. Our best effort doesn't disturb it. But there are enough examples where we need to worry about the performance. And here it was just a very small example, again, with two switches. In a longer network, this curve has a way longer tail. But we want to get rid of that. And now if we enable frame preemption, you see that the critical traffic has a way thinner area of transmission. And our best effort, we couldn't really showcase that in the upper picture, but here we see now that some frames of the best effort are immediately sent. So we injected somewhere on the path. That's why it looks like it has no latency. But some frames are still immediately sent, while quite a set of frames is now preempted and therefore has a higher latency. So this orange curve here are all the preempted frames that are preempted by the express traffic. So with that, you see that the impact of the frame preemption reduces the spread of the transmission. You achieve results closer to the best case with frame preemption. Important to know is that if you configure the task correctly, packets can flow along the path without interference or with just a little interference, so almost no queuing delays. The complexity to configure the task is quite complex, and it costs resources. So scheduling the time-aware shaper results in downtimes on your link. It results in times where frames are in the queue but cannot be sent because other priorities turn. But if you have the resource available, that's a very good feature. And more switches on the market support that feature. So yeah, to just do some advertisement, also the latest releases of the Belden switches, they also support the time-aware shaper. And for the frame preemption, it's way easier to configure because you just need to assign the priorities to the different classes, express or preemptible, and it enhances the performance already quite a lot. And as a result, the lower priority traffic is additionally delayed, but typically for the lower priority traffic, You just have requirements in terms of delivery, so bandwidth, you need to deliver it, but the latency isn't that important, at least not in this factor here, and therefore it's acceptable. So now, quickly, let's have a look at the TSN mechanisms in general, looking specifically at the IEC IEEE 60802, the TSN profile for industrial automation. They select features from the Q standard to create guarantees, schedule traffic, frame preemption, strict priority. They also introduce disciplining features, retagging, reprioritization, rate limiting on ingress ports of your network. And also they talk about reliability. So here are quite a number of additional features. And the IEEE 60802 is a profile that basically needs to solve a broad use case for the industrial automation. It's based only on IEEE and ITF specifications, covers QoS, robustness, reliability, and important, the configuration interfaces. Now with UAFX, we do not want to reinvent the wheel. UAFX builds on top of that's a mistake here. It's the 6802. Should be there. It basically is applied for all the topics in networking that we do. So we do not reinvent the wheel. Very likely, I mean, standardization is still ongoing, so no guarantees, but very likely the 6802 is quite compatible with what we do in UAFX. In UAFX, we define different network facets to make it easier for the selection of features so that you do not need to choose all the features by itself. I just presented 2 examples and listed quite a lot more. We group these in the different facets. We have the base facet, advanced facet, and full facet. So most dominant example, in the advanced facet, we have the frame preemption available. In the full facet, we have the frame preemption and the time-aware shaper available. We will do exactly the same for also the end stations. So we will add that now in the current work on the C2D. And UAFX per default always uses UDP, but also allows the Ethernet option. So the more time-critical applications, probably not all, but probably a lot of them will use more the Ethernet. The UDP is then for all the not too time-critical communication. That is maybe a figure you have already seen, but I want to repeat it because I think it's very important when you talk about different features and to understand that also if you have devices of different categories, it fits together. With that figure, we want to show that the quality of service or the set of features that you can use has a graceful degradation, meaning that you always achieve the worst between 2 points. So looking at this example, we have here different networks, they're connected, and now this yellow, and yellow is the advanced facet, this yellow device wants to talk to that yellow device. And in between, you have green, yellow, green, and again yellow. Green is the full, advanced is lower, it's just the advanced, and therefore the best you can achieve is the advanced. The same accounts for combining a blue, so the base devices to each other. If you're in between, just have the same or higher set of features with your facets, you can always achieve your required set of features, and then with that also quality of service. And the same accounts for brownfield. We make sure that any brownfield that is not TSN aware still works over our network and is not out of order by that. So you can reuse existing components with the guarantees that you already have today, not with more. So now, quick summary on that first block. How will OPC UA FX achieve a higher performance? First, we define different device categories: motion, I/O, and instrumentation. We define different TSN network access facets on the end devices, and we define different TSN bridge facets. So now with that, you can combine quite a lot to solve all your different specific scenarios. But this adds complexity. So to reduce the complexity, we now in the networking working group of UFX started to write a white paper. The white paper probably will not be published, but in the white paper, we will have a look at very different use cases and then figure out which of these combinations are actually useful. And we will identify the most valuable combinations and suggest to include them in the standard. So when you then use the standard, you already have a good set of combinations available, and you don't need to think about all the details of the features. That is all pre-selected for you and pre-engineered for you. So with that, we provide a seamless integration, basically. Now coming to the last block, it's a shorter one, so we'll finish still in time. How to enable network convergence. Basically, network convergence means we want to connect everything together in the same network without complexity for the engineer. So let's quickly have a look at what convergence means. We can have different types of applications. Either we have a legacy deployment where you have an isolated machine network with your industrial protocol. You have a PLC as a gateway. Second scenario is, and that's now basically, I would say, the next gen deployment. You have a mixture of your industrial protocol and OPC UA FX. So some end devices still only talk the existing protocols with the yellow. Some already talk a combination of OPC UA, UAFX, and the industrial protocol. So you have a mix of traffic in the network. And then a futuristic case where we are on the path to that for some deployments, for some scenarios, a full UFX deployment if you wish to install something like that. But now the middle case and also the backbone here, that are now the interesting pieces where it gets complex if you want to combine these. And there we quickly have a look within the configuration on what you can set and how that actually results in the frames. So if you look at a part 14 configuration, you have the writer group. In there you can specify the network interface, the transport type. I now selected the Ethernet UADP. Then you can select the QS category and the priority label. So the QS category is something that we introduced in part 14 with the last release. You can set at the moment only priority. We work on additional ones. I will showcase that on the next slides. Priority means that you automatically have another field called priority label. And there you can set a priority label. UAFX will define that set of labels that are available to you. But this label doesn't mean anything for the priority values in the frame. This label is here that the engineer has an easy life to choose this label because it's understandable, it's comprehensive. You can, it's a named label and therefore it's easy to select for an engineer. Now, on the network side, that is something the application engineer does not need to do. That is something the network administrator configures. You have your network interfaces, the default interface, then maybe a VLAN interface added to that with VLAN ID 100. And then there is the priority mapping table. That mapping table can be configured in the future via netconf. So it's for the application, for the network engineer, configurable throughout the whole network. On all devices, it will be the same mapping table. So all devices will behave exactly the same. And now the network interface binds to that, and by that you have a link to the respective mapping table. And the stack automatically then looks up the category and label, figures out, I need, we are in the Ethernet case, so we need a PCP value of 7. And when the stack crafts the network message, it can insert the VLAN ID, it can insert the PCP value, and as we have a UADP connection, it also inserts the ether type of the UADP. And with that, the application engineer just stated that it's high criticality of the traffic. Nothing more. The network engineer decides on which priority value. Maybe for the 7, it sounds obvious that 7 is the highest one. But depending on how you configure your TSN mechanisms, on which traffic class is assigned to which time-aware shaper slot, maybe 7 is not the smartest for the most critical one. Or maybe you have another one in the express category for frame preemption. Therefore, that is something the network administrator does consistently across all the devices, because the network administrator knows what he or she did on the switches, and the application engineer just states something meaningful for the criticality. If we now look at the connection establishment of UAFX, you have already seen in previous videos probably that there is a connection manager. The connection manager contains the final UAFX connection. The connection manager connects to the functional entity that then create the pub sub configuration. Within, there's always this red dot. The red dot is the selected quality of service within the UAFX connection. Here we set the category is again priority, and the priority label is green. So in the first UAFX release, we specified the label green. Green maps per default to PCP4 and is for cyclic but unsynchronized communication. And now, when the functional entity sends data with the pub sub configuration, there is the mapping table, as you can see here in the middle. Priority green maps to 4, and that is then transferred over the wire. So the network administrator is aware of all the labels in the network, can configure the network accordingly, set the priority values accordingly, and then the system works fluently. So that is already supported in the controller-to-controller release. Now, as you can imagine, a network administrator needs to have a look at which priority labels are available, needs to adjust the switches. That's inconvenient. So in the next versions, we will work on including the concept of a CNC, Central Network Controller. That is a concept introduced by the IEEE. The connection manager announces which priority labels are used to the CNC. The CNC automatically configures the switches, updates the mapping tables, so nothing manually to be done. And then you can have the communication again. In this case, for example, it's QS category deadline, and the label is motion. So for example, motion traffic, you then want a mapping to PCP7. And one important remark, so we are working on that for the C2D release, is we are working for 3 additional categories in the future: bandwidth, latency, and deadline, as we identified these as the most urgent ones. So a quick summary: how does OPC UAFX enable convergence? We have in part 22, the base network model, these mapping tables. It decouples application from network configuration. We have different types of applications that can be mapped to the specific settings in the network without the application engineer being aware of that mapping and the difference in the network. The mapping depends on the selected TSN mechanisms. So we do not want to propose a fixed mapping. We propose a default mapping, but it's not fixed because it really depends on what you finally do in the network. So depending on the specific scheduling, shaping, policing configurations, you want adjustment to that. The engineering workflow enables that mapping. So it's fully compliant with the UAFX engineering workflow. And in the next releases, we will enable this automation that it's more fluent for the administrators. So with that, we are already at the end of this webinar. I have basically 3 key takeaways that are important to remember. In general, OPCUA offers performant communication if you select the correct stack and mechanism to craft the messages. It allows very flexible communication for monitoring, connection to IT systems, but also for the control applications. So therefore, OPCUA is very powerful, using the same model for different kinds of connections. We enable network convergence by decoupling the application from the network configuration. And the next OPCUA releases with the CNC will include seamless use of TSN mechanisms, a more advanced mapping. And it's not just there on slides and in Word documents. We also have running prototypes. Here in the picture, you see a fair demonstrator. So, for example, if you're on the Hannover Fair, I think we will show that again. So just come by the OPC Foundation booth and learn on what we did there already. The UFX has a prototyping working group where you can learn more on that and you can contribute with your experience from the field. Also contribute with prototypes and experiments on this topic to improve the whole system. And in general, again, the invitation, join the LinkedIn group, subscribe on YouTube to just stay aware of what we educate further on UFX. And with that, thank you for the attention. And now we still have a little time, about 7 minutes left for Q&A. And if there's more interest in specific topics, we will schedule follow-up webinars on that. Perfect. Now let's see if I'll just wait for somewhere to have the questions pop up, I assume. Okay. So it doesn't seem that there are questions coming in so far. With that, thank you again for the attention. Thanks for joining this UFX Professionals webinar. Also, thanks for the organization to Tunga. And then see you soon in one of the next webinars. Thanks for joining.